Hello everyone. This is Dr. Piyali Sengupta from Department of Civil Engineering of Indian Institute of Technology Dhanbad. I welcome you all to the course on bridge engineering. The fourth module of this course is on steel truss bridges. In the first class under module 4, we had discussed about basic features, structural configurations, design principles, and influence line diagram of steel truss bridges. In today's class, we are going to see design example of a steel truss bridge. Let's see what we are going to learn in today's class. We are going to take a design example in this class so as to learn about the steps involved in the load calculation and design of a steel truss bridge. The problem statement of the design example says we are required to design a steel truss bridge for effective span of 30-meter, carriageway width for two lengths of 7.5 meter, curb width 600 millimeter. The loading type is IRC class AA tracked vehicle. Materials to be used are M25 concrete and Fe415 reinforcement for deck slab and rolled steel sections with an yield stress of 250 MPa for stringer beams and cross girders. So the given data we had already discussed. The first task that we are going to do is arrangement of the members. For a span of 30 meter, we can proceed with providing a warren truss with 6 panels with each of the panel having a equal length of 5 meter. We can provide cross girders at 5 meter intervals joining the nodal points. The stringers can be placed at 1.875 meter centers. The configuration of the warren truss and the arrangement of cross girders and stringer beams can be shown through the diagram. So we can see the configuration of the warren truss consisting of 6 panels with each of the panel having a length of 5 meter. The warren truss has a height of 5 meter. We can see the cross section of the deck showing the steel truss here, plate girder for cross girders and stringer beams as I sections, rolled steel sections. Then we can see the deck slab marked as 200 millimeter depth, wearing coat of 100 mm thickness, curb width 600 millimeter. The stringer beam has a spacing of 1.875 meter uniformly. Also, the carriageway width is marked as having 7.5 meter. So let's come to the next step, that is dead load calculation for deck slab. We are going to first design the deck slab, and that's why in this step we are going to calculate the dead load for the deck slab. The self weight of the deck slab of 200 millimeter thickness will be calculated as 0.2 times 24, that is equals 4.8 kilonewton per meter square. Here 24 kilonewton per meter cube is considered to be the unit weight of reinforced concrete. Next, the self weight of the wearing coat of 100 millimeter thickness can be calculated as 0.1 times 22, that is equals 2.2 kilonewton per meter square. Here 22 kilonewton per meter cube is considered to be the unit weight of the wearing coat material. So the total dead load per area will be 4.8 plus 2.2, that is equal to 7 kilonewton per meter square. Next, we can calculate the total dead load on the slab panel by considering this dead load per area multiplied by the area of the panel. So that is equals 7 times 5 meter times 1.875 meter. So that turns out to be 65.625 kilonewton. Next, for dead load bending moment calculation, we are going to use Pigot's coefficient method that we had discussed in module 2. So using Pigot's coefficient method for dead load, since it is uniformly distributed on the deck, so the dispersion of the dead load along the short span direction and long span direction will be all throughout. So U by B will be equals 1 and V by L will be equals 1 as well. So next we are required to calculate K. K is taken to be the ratio of B by L, and B by L is considered to be equal to 1.875 divided by 5. That turns out to be 0.375, and that is approximated to be 0.4. So by using Figures coefficient method, we can go to refer the charts for k equals 0.4. So if we try to locate u by b and v by l equals 1, m1 times 100 turns out to be at this point, and similarly from the second chart, m2 times 100 gives us this much value for u by b equals 1 and v by l equals 1 as well. So if we read the values, m1 and m2 turns out to be having a magnitude of m1 equals 0.045 and m2 equals 0.009. So once we are done with determination of m1 and m2, we can calculate the bending moment in the short span direction due to dead load as equal to W times m1 plus mu m2, where W is the total dead load in the panel, that is 65.625 kilonewton, m1 and m2 that we have just now computed, and mu stands for the Poisson's ratio for concrete, that is taken to be 0.15. So by applying the magnitude of all the parameters, we find out that dead load induced bending moment in the short span direction will be 3.042 kilonewton meter in the panel. Similarly, the bending moment in the long span direction due to dead load can be obtained as W times M2 plus mu M1. So we can apply the magnitude of the parameters in the expression so as to determine the bending moment in the long span direction due to dead load equals 1.034 kilonewton meter. Now, the deck slab is continuous. Due to the continuity effect, the design bending moment along the short span and long span direction can be computed as 0.8 m1 and 0.8 m2 respectively. So 0.8 m1, that is the dead load induced bending moment in the short span direction, keeping in mind continuity effect, will be equals 0.8 times 3.042, that is equals 2.434 kilonewton meter. Similarly, the design bending moment along the long span direction due to dead load will be equal to 0.8 times m2, that is 0.8 times 1.034 kilonewton meter, and that is equal to 0.827 kilonewton meter. Shear force due to dead load can be obtained by using the fundamentals of mechanics, that is equal to 7 kilonewton per meter square dead load times 1.875 meter minus of 0.01 meter divided by 2, that is equal to 6.527 kilonewton. Here 0.01 meter is the width of the stringer beams. The next step will be calculation of the live load for the deck slab. Now the live load is given to be IRC class AA tracked vehicle, which has a wheel imprint dimension of 3.6 meter times 0.85 meter. Each of the wheel exerts a loading of 350 kilonewton and the impact factor is 1.25. So if we place a single wheel at the center of the panel of the deck slab, then we can easily compute that K equals 0.4, that we have already computed. So wheel load dispersion in the short span direction U will be equal to 0.85, that is wheel imprint in that direction, plus 2 times wearing core thickness, that is equals 0.1 meter. So 0.85 plus 2 times 0.1 equals 1.05 meter. Similarly, wheel load dispersion along the long span V can be obtained as wheel imprint in that direction plus 2 times wearing core thickness, that is 3.6 plus 2 times 0.1, that is equal to 3.8 meter. Now, since we already know that L equals 5 meter and B equals 1.875 meter, we can easily compute U by B and V by L from the calculated values of U and V. So U by B turns out to be 0.56 while V by L turns out to be 0.76. In the diagram, you can see that the slab panel is shown having B equals 1.875 meter and L equals 5 meter, and the wheel load dispersion along short span direction U equals 1.05 meter and V equals 3.8 meter. V stands for the wheel load dispersion along the long span direction, and the dispersed area is shown in this diagram through the shaded area. So for k equals 0.4, u by b equals 0.56 and v by l equals 0.76, we can determine the magnitude of Pigot's coefficients m1 and m2 from the Pigot's charts. We can refer to the same chart for k equals 0.4 and then we can look for u by b equals 0.56 and v by l equals 0.76, and that leads us to this point for m1 and this point for m2. And if we read the chart properly, we will see m1 turns out to be 0.083 and m2 turns out to be 0.018. So once we have computed m1 and m2, the bending moment in the short span direction m1 due to live load can be obtained as W times m1 plus mu m2, where W is the wheel load, that is equal to 350 kilonewton. M1 and M2 we have computed, and mu stands for Poisson's ratio for concrete, that is equal to 0.15. So the bending moment in the short span direction due to live load will be equals 29.995 kilonewton meter. Similarly, the bending moment in the long span direction M2 due to live load can be calculated as W times M2 plus mu M1. Here we know the magnitude of all the parameters, and once we put the values in the expression, we will see that the bending moment in the long span direction will be equal to 10.657 kilonewton meter. For continuous slab, keeping in mind continuity effect, we are required to apply a factor of 0.8 to the live load applied along the short span and long span. Along with that, we are required to include impact factor with the live load. So the design bending moment due to the live load along the short span, including the continuity effect and impact factor, will be 0.8 times m1 times 1.25. So that is equal to 29.995 kilonewton meter. Similarly, the design bending moment due to live load along the long span direction, including impact factor of 1.25 and continuity effect, we are going to see the magnitude for design bending moment turns out to be 0.8 times m2 times 1.25, that is equals 10.657 kilonewton meter. Next, the effective width method can help us in computation of the dispersion of live load in the short span direction. That can be done as x plus 2 times d plus h, where x is wheel imprint dimension, it is 0.85 meter, d stands for wearing core thickness, that is of 0.1 meter, and h stands for the slab thickness, that is 0.2 meter. So once we apply all the magnitude, we will see that the effective width method will give us wheel load dispersion along short span equals 1.45 meter. Now, for maximum shear in the deck slab, the wheel load is required to be placed such that the center of the wheel is at 1.45 divided by 2 equals 0.725 meter apart from the edge of the panel. Now, effective span for shear force calculation L will be 1.875 minus of 0.01. The 0.01 meter stands for the girder width, that is equals 1.865 meter, and effective breadth D equals 5 minus 0.01, that is equals 4.99 meter. Span ratio of the slab D by L will be equals 4.99 by 1.865, and that is equals 2.676. Now, effective width of the slab using effective width method can be obtained by this expression kx times 1 minus x by L plus Bw. We are familiar with this expression because we had discussed this in module 2. Now, K is a constant that is dependent on the ratio of B by L, and we can read this table from Annexure B3 IRC 112-2011 that for B by L values ranging from 0.1 to 2 and above, we can determine the magnitude of K for simply supported and continuous slabs. Here, in our case, K value can be obtained for continuous boundary condition of the slab and B by L ratio is above 2. So, the K value will be 2.60. So, here that is what we had determined for B by L equals 2.676. Next, BW is wheel contact dimension in a direction perpendicular to the span of the slab plus 2 times wearing core thickness. So BW can be obtained as 3.6 plus 2 times 0.1. So that is equals 3.8 meter. X is the distance between CG of the wheel to the nearest support that we had already calculated to be 0.725 meter. So we can determine the effective width of the slab from this expression once we apply the magnitude of all the parameters. And that value turns out to be 4.952 meter once we put all the values in the expression. Now, effective length of the load can be obtained by using effective width method using the expression x plus 2 times d plus h, where x equals 3.6 meter, d equals wearing core thickness 0.1 meter and h is slab thickness that is 0.2 meter. So that is equals 4.2 meter. So live load per meter width due to 350 kilonewton wheel load will be 350 by effective width of 4.952 meter. So that is equals 70.678 kilonewton per meter width. So from there, maximum shear force due to live load, including impact factor, can be obtained as 70.678 times 1 minus 0.725 divided by 1.865. That needs to be multiplied by impact factor of 1.25. So this calculation is done using the fundamentals of mechanics, and that is equal to 54.003 kilonewton as maximum shear force due to live load. Now, service level bending moment in the slab arising from dead load and live load in the short span direction MB will be equal to simple summation of dead load moment plus live load moment in the short span direction, that is equals 32.429 kilonewton meter. Now, service load bending moment in the slab arising from dead load and live load in the long span direction ML can also be determined by considering simple summation of dead load bending moment and live load bending moment along the long span direction, that is equals 11.484 kilonewton meter. Service level shear force in the slab from dead load and live load can be obtained as simple summation of dead load shear plus live load shear, that is equals 60.853 kilonewton. Next, we can go for ultimate design bending moment in the short span direction in the slab. That can be calculated by applying 1.35 factor to the dead load bending moment plus 1.5 as load factor with the live load bending moment. So it is obtained as 1.35 times dead load bending moment plus 1.5 times live load bending moment, that is equal to 48.278 kilonewton meter. Similarly, ultimate design bending moment in the slab in the long span direction will be 1.3 times dead load bending moment plus 1.5 times live load bending moment, that is equal to 17.102 kilonewton meter. Ultimate design shear force in the slab arising from dead load and live load will be 1.35 times dead load shear plus 1.5 times live load shear, that is equals 89.816 kilonewton. The subsequent step will be design of the slab. Now overall depth of the slab approximated to be 200 millimeter. So if we assume 40 millimeter clear cover and 12 millimeter diameter of the bar to be used, effective depth of the slab will be 200 minus 40 minus 12 by 2, that is equal to 154 millimeter of effective depth. Now, if we use M25 grade concrete and Fe415 HYST bars as prescribed in the problem statement, the limiting moment of resistance along the short span direction or singly reinforced sections will be 0.138 FCK BD square. And effective depth of the slab required can be obtained by rearranging the terms. So, the effective depth of the slab required can be obtained as square root of m by 0.138 FCK B, where m can be considered to be the design ultimate bending moment in the short span direction in the slab arising from dead load and live load, and that is equals 48.278 kilonewton meter that we have just now calculated, and we have to multiply it by 10 to the power 6 so as to convert it into the requisite unit system. And FCK for M25 grade concrete is 25 MPa and B is taken to be unit meter, that is 1000 millimeter. So by calculation we find out that effective depth of the slab required is 119 millimeter. So we have provided our effective depth of the slab to be 154 millimeter, while the requirement is only 119 millimeter. So since the depth of the slab provided is higher than the depth required, we can deduce that the section is under reinforced. The area of the reinforcement required to resist the ultimate bending moment can be computed using this expression that we are already familiar, where mu ultimate moment is considered to be 0.87 FYAST multiplied by d minus of FYAST by FCKB. Here Fy is characteristic strength of steel, AST is area of the steel, D is effective depth, B is unit meter with FCK is characteristic compressive strength of concrete. So if we apply the magnitude of all the parameters and rearrange the term, we can see that it is turning into a quadratic equation of area of the steel AST in the form of ax square plus bx plus c equals 0. We can easily solve for it, and from the two roots we can look for the suitable root, and that gives us area of the steel required to be 969.553 millimeter square. So if we consider using 12 millimeter diameter bars as main reinforcement, the spacing S can be obtained as 1000 times small AST by capital AST, where small AST stands for area of a single bar having a diameter of 12 millimeter. So that is pi by 4 times 12 square. So we can see by providing the magnitude of the terms, we will see that the spacing is 116.648 millimeter. Therefore, we can proceed with providing 12 millimeter diameter bars at a spacing of 100 millimeter. So once we change the spacing, the area of the steel provided will be different from what is required. And what is the amount of the steel provided? That can be obtained by rearranging the terms in this expression. So here the actual area of the steel provided AST can be obtained as 1000 small AST by S. So that is what is done here, and that gives us to 1131 millimeter square as the area of the steel provided. Similarly, if we use M25 grade concrete and Fe415 HYST bars, we can determine the area of the steel required by using the same expression for the bending moment in the long span direction. So if we apply all the parameters magnitude in the expression and rearrange the terms, we will see that it is turning into a quadratic equation of AST which can be solved, and the area of the steel required along the long span direction will be 318.51 millimeter square. Using 10 millimeter diameter bars as main reinforcement, the spacing given by will be S equals 1000 small AST by capital AST. We know that small AST stands for the area of a single bar of 10 millimeter diameter, that is equals pi by 4 10 square. So we can apply the magnitude of small AST capital AST, and the spacing turns out to be 246.586 millimeter. We can proceed with 10 millimeter diameter bars at 150 millimeter spacing along the long span. So the actual area of the steel provided can be obtained by rearranging the terms in this expression, and that is obtained as 1000 small AST by S. So that is done here, and then the area of the steel provided is determined as 523.6 millimeter square. Next, we are required to check for ultimate flexural strength. The ultimate bending moment of the deck slab MU equals 0.87 FYAST times small d minus FYAST by FCKB. Once we apply the magnitude of all parameters, we will see that the ultimate flexural strength turns out to be 55.219 kilonewton meter, which is higher than 48.278 kilonewton meter. So it is safe. The ultimate shear strength of the deck slab can be obtained VRDC equals 0.12 K times 80 rho 1 FCK to the power 0.33 times BD. Here K can be obtained as 1 plus square root of 200 by D, that is equals 1 plus square root of 200 by D stands for effective depth of 154 millimeter, that is equals 2.14. However, K can be having a maximum value of 2. So we can consider K to be 2 here, and rho 1 is the area of the main reinforcement along the short span direction, that is obtained as AST by BD, that is 1131 divided by 1000 times 154, that is equals 0.007. So once we apply the magnitude of all the parameters in the expression, we can determine that the shear strength of the section is 88.299 kilonewton. So that is marginally unsafe because the ultimate shear force in the section is 89.816 kilonewton. So due to this marginal gap, we can change the reinforcement amount by altering the main reinforcement spacing as 90 millimeter. So if we go for providing 12 millimeter diameter bars at a spacing of 90 millimeter, so the area of the steel provided gets updated to 1256.633 millimeter square. Rho 1 in this way gets updated to 0.008 in place of 0.007. So now if we apply the changed value of rho 1 in this expression, then the ultimate shear strength of the section turns out to be 92.277 kilonewton, which is higher than the ultimate shear force. So the section is found to be safe. Next step is to go for limit state of cracking. IRC 112/2011 prescribes us with a permissible crack width of 0.3 millimeter in reinforced concrete members under moderate exposure condition. So we can read table 12.2 and table 12.3 so as to look for the maximum bar size and maximum bar spacing for the service stress in the steel for permissible crack width of 0.3 millimeter. So first we are required to determine the service stress. For that, service load bending moment we know equals 32.429 kilonewton meter along the short span direction. The stress in the steel at working load can be obtained as M by D minus X by 3 times AST, where X is neutral axis depth. We are familiar with M, D and AST. So first we need to determine neutral axis depth. Neutral axis depth can be determined by considering compression force equals tension force, and that is equals Bx square by 2 times EC equals ES times AST times D minus X. So from this expression, once we apply the magnitude of all the parameters, then X turns out to be 46.493 millimeter by solving the quadratic equation of X. So we can apply the magnitude of M small d, X and AST so as to determine the service stress to be 186.324 MPa from this expression. Now for service stress 186.324 MPa and permissible crack width of 0.3 millimeter, we can go back and refer to the table. So it should be obtained by a linear interpolation in between the two values 160 and 200. So by linear interpolation, we can find out that the maximum bar size that can be used is 27 millimeter and maximum bar spacing permissible is 267 millimeter. Here we have reinforced the slab with 12 millimeter diameter bars at 90 millimeter spacing. So the bar size and the spacings are within the permissible limits of control of cracking. Next, we can go with design of stringer beams. Now, for that, first we need to go for calculation of dead load. The dead load due to sulfate of the slab and wearing coat we have already computed to be having a loading of 7 kilonewton per meter square. So 7 times 1.875 will be the dead load due to sulfate of the slab and wearing coat. That is equals 13.125 kilonewton per meter. Sulfate of the stringer is approximated to be 1 kilonewton per meter. The total dead load then on the stringer is equals 13.125 plus 1, that is 14.125 kilonewton per meter. Now maximum bending moment due to dead load can be obtained as 14.125 times 5 square by 8, that is equal to 44.141 kilonewton meter. Now, the maximum shear force due to dead load can be obtained as 14.125 times 5 by 2, that is equal to 35.312 kilonewton. Next, the stringer is subjected to maximum bending moment when one of the wheel is directly on it such that CG of the loading is coinciding with the CG of the beam, as we can see in this diagram, that the loading having a wheel imprint dimension of 3.6 meter is placed such that CG of the loading is coinciding with the CG of the beam. So in this condition, for the position of the live load for maximum bending moment, we can determine the bending moment that can be obtained by using simple fundamentals of 0.5 times 350 times 2.5 minus 0.5 times 350 times 0.25 times 3.6. That gives us 280 kilonewton meter. If we are not able to memorize the formula involved, please do it from first principle. That is always useful because we can first have the loading diagram ready, then we can go for drawing the shear force diagram, and area of the shear force diagram will give us the bending moment diagram. So from there, once we draw bending moment diagram, we will be able to identify what is the maximum bending moment. Now, the maximum bending moment due to live load, including the impact factor of 1.25, can be obtained as 280 times 1.25, that is equal to 350 kilonewton meter. The stringer is subjected to maximum shear force when one of the track is placed at the support. Now, the wheel has an imprint dimension of 3.6 meter. So it means that the CG of the wheel is placed at 3.6 by 2, that is 1.8 meter from the edge. So that's why the CG from the nearest support has a distance of 1.8 meter, while the other edge has a distance of 3.2 meter as shown in the diagram. So the maximum shear force due to live load will be 350 times 3.2 by 5, that is equal to 204 kilonewton. Now, maximum shear force in the stringer beam due to live load, including impact factor of 1.25, will be equal to 224 times 1.25. That is equal to 280 kilonewton. The ultimate design bending moment arising from dead load and live load can be obtained by considering 1.5 times dead load bending moment plus 1.5 times live load bending moment. That is equal to 591.212 kilonewton meter. The ultimate design shear force from dead load and live load can be obtained similarly by considering 1.5 times dead load shear plus 1.5 times live load shear. That is equal to 472.968 kilonewton. Now, for compact sections under simply supported boundary conditions, design bending strength MD can be taken as 1.2 times ZE times Fy by gamma m0, where ZE stands for elastic section modulus of the cross section, Fy stands for yield stress of the material, that is equal to 250 MPa. Gamma m0 is the partial safety factor of the material, that is equal to 1.1. So this MD is expected to be higher than the design bending moment M for a safe section. So we can try with a wide flange beam section ISWB 550, which is going to have a ZE of 2720 millimeter cube. So design bending moment for this section MD obtained as 1.2 times ZE times Fy by gamma m0 can be obtained by providing the magnitude of all the parameters. And that turns out to be 741.818 kilonewton meter, which is higher than the design bending moment of 591.212 kilonewton meter. Hence our design is safe. Then we will check for the shear. The design shear strength VD is taken to be equal to Vn by gamma m0, and this is expected to be higher than design shear force V. Now, Vn stands for nominal shear resistance of the section, that is taken as AV times Fyw divided by square root of 3. Here, gamma m0 is partial safety factor against shear failure, that is taken to be 1.1. AV stands for shear area, that is equal to H times EW for hot roll sections. Fyw stands for yield strength of the wave, that is equals 250 MPa. H stands for overall depth of the section, that is equal to 550 millimeter. TW stands for thickness of the wave, that is equals 10.5 millimeter. So Vn equals AV times Fyw divided by square root of 3 can be easily obtained by providing the magnitude of each of the parameters. And that turns out to be 833.549 kilonewton. So design shear strength Vd can be equal to nominal shear strength Vn divided by gamma m0, that is equal to 833.549 divided by 1.1. So that is equals 757.772 kilonewton, which is higher than design shear force 472.968 kilonewton. Hence our design is safe. Next, we can proceed to design of cross girders. The span of the cross girders are 7.5 plus 2 times 0.6, that is arising from the curve width, that is equals 8.7 meter. Dead load due to slab and wearing coat will be equal to 7 times 5, that is equal to 35 kilonewton per meter. Dead load due to stringer beams will be 1.125 times 5, that is equal to 5.625 kilonewton. Load due to connectors will be equal to 0.375 kilonewton. Total dead load turns out to be 5.625 plus 0.375, that is equal to 6 kilonewton. Then sulfate of the cross girder can be obtained as 0.2 times L, plus 1, that is equal to 0.2 times 8.7 plus 1, that is turning out to 2.74 kilonewton per meter. That can be approximated as 3 kilonewton per meter. So the total uniformly distributed loading will be 35 kilonewton per meter plus 3 kilonewton per meter, that is equal to 38 kilonewton per meter. So the maximum dead load bending moment at the center of the span can be obtained once we identify the position of the dead load for maximum bending moment. Now this is the loading diagram. From the loading diagram, we can proceed with drawing the shear force diagram, and subsequently we can draw the bending moment diagram that is going to help us in identifying what is going to be the maximum dead load bending moment, and that is going to give us 391.028 kilonewton meter. Now maximum dead load shear at support can be obtained as 38 times 8.7 by 2 plus 6 times 5 by 2. We can also obtain it from the shear force diagram that turns out to 180.3 kilonewton. Now span of the girder is 8.7 meter. We are going to consider impact factor on the girder as 1.4. The maximum live load bending moment including impact factor occurs when the two tracks of IRC class AA tracked vehicle are spaced symmetrically from the center of the cross girder. So this is going to be the position of the live load for maximum bending moment, where each of the wheels are positioned equidistant from the center of the cross girder. This distance is 2.05 meter. We know that for IRC class AA tracked vehicle, the inner edges have a distance of 1.2 meter and each of the wheel has a wheel imprint dimension of 0.85 meter. So 1.2 plus 0.85 gives us 2.05 meter. So maximum bending moment for this loading position can be obtained by drawing the shear force diagram from the loading diagram and subsequently drawing the bending moment diagram. And once we draw the bending moment diagram, we will see that the maximum bending moment turns out to be 1163.75 kilonewton meter. Maximum bending moment for the live load, including the impact factor of 1.4, will be 1.4 times 1163.75, that is equal to 1629.25 kilonewton meter. The maximum shear force due to the live load occurs when one of the edge of the wheel is 1.2 meter from the curve. 1.2 meter is the minimum clearance that we require to provide. So this means that the center line of the left wheel is at 0.6 meter is the curve width plus 1.2 meter plus 0.85, that is wheel imprint dimension, divided by 2, that is equal to 2.225 meter from the left support. Also, we can determine that the left wheel is 8.7 minus 2.225 meter, that is 6.475 meter from the furthest support, that is right support. Similarly, we can calculate the center line of the right wheel, that is equal to 6.475 minus of 1.2 minus of 2 times 0.85 by 2, that is 4.425 meter from the furthest support. So for this condition, the maximum shear force due to live load can be determined by using the fundamentals of mechanics. We can draw the loading diagram, then subsequently we can draw the shear force diagram. So the maximum shear force due to live load turns out to be 438.506 kilonewton. By applying impact factor of 1.4, the maximum shear force upgrades to 1.4 times 438.506, that is equal to 613.908 kilonewton. The ultimate design bending moment from dead load and live load can be obtained as 1.5 times dead load bending moment plus 1.5 times live load bending moment, that is equal to 3030.417 kilonewton meter. Similarly, the ultimate design shear force from dead load and live load can be obtained as 1.5 times dead load shear plus 1.5 times live load shear, that is equal to 1191.312 kilonewton. So first we can proceed with considering a trial section for the weight plate of the plate girder. The optimum depth of the plate girder is obtained as mk divided by fy to the power 0.33 when intermediate transverse stiffeners are not to be provided. Here k is taken to be d by tw, that is considered to be 180 for thin webs, and fy is 250 MPa, that is given in the problem statement. So by substituting the requisite parameters magnitude as m, k and fy, then we find out that the optimum depth of the plate girder turns out to be 1207.301 millimeter. Also, optimum wave thickness of the plate girder TW is taken as m by fy k square to the power 0.33. Here also k equals d by tw equals 180 for thin webs and fy equals 250 MPa. By substituting the magnitude of all the parameters, we can determine tw equals 3030.417 times 10 to the power 6 divided by 250 times 180 square to the power 0.33. That is going to be 7.065 millimeter. So we can try to consider wave plate having a dimension of 1200 millimeter depth and 10 millimeter thickness. Let's go for trial section of flange plate then. We assume that the bending moment will be resisted by the flanges and the shear force by the wave. So the required area of the flange of the plate girder AF can be obtained as M times gamma M0 divided by Fy times D, where gamma M0 is the partial safety factor. We have already approximated D to be 1200 millimeter for the wave plate of the trial section. Gamma M0 is taken to be 1.1, Fy is 250 MPa. So once we apply the parameter of all the magnitude, area of the flange AF turns out to be 11111.529 millimeter square. Now if we assume that the flange width BF will be equal to 0.3 times depth of the girder D, the flange width BF will be 0.3 times 1200, that is equal to 360 millimeter. So if we consider that the flange width BF will be 400 millimeter, flange thickness TF turns out to be AF by BF, that is equal to 27.779 millimeter. So we can try to consider flange plates of dimension 400 millimeter width times 30 millimeter thickness. So the overall depth of the plate girder T turns out to be depth of the girder plus 2 times flange thickness, that is equal to 1200 plus 2 times 30, that is 1260 millimeter. Now the classification of flanges can be performed now. Outstand of the flange B will be BF minus TW by 2, that is equal to 400 minus 10 by 2, that is equal to 195 millimeter. Now B by TF will be equal to 195 by 30, that equals 6.5, which is less than 8.4. So the flanges are going to be plastic. Now we can check for the bending strength. The plastic section modulus ZP can be obtained as 2 times BF times TF multiplied by D minus TF by 2. Here D is the overall depth. So we can determine the magnitude of ZP by applying the magnitude of all the parameters. So that turns out to be 14760000 millimeter cube. The moment capacity MD can be obtained as Zp times Fy by gamma M0, where gamma M0 is taken to be 1.1. Zp we have just now computed. So the moment capacity turns out to be 3354.545 kilonewton meter, which is higher than the ultimate design bending moment M equals 3030.417 kilonewton meter. So we can deduce that the trial section is safe in terms of the bending strength. Next, let's check for the shear capacity of the wave. D by TW is 1200 by 10, that is equal to 120, which is less than 200. So elastic critical shear stress tau CRE can be obtained as kV pi square E by 12 times 1 minus mu square times D by TW square. Here kV equals 5.35 when transverse stiffeners are provided only at the supports. Mu is Poisson's ratio equals 0.3. Elastic critical shear stress then can be obtained by providing the magnitude of all the parameters. That turns out to be 67.158 MPa. Now, non-dimensional wave slenderness ratio for shear buckling stress, tau W, can be obtained as square root of Fyw divided by root 3 times tau CRE. So that can be obtained as 1.466, which can be approximated as 1.4, which is greater than 1.2. So shear stress corresponding to buckling for tau W greater than 1.2 will be obtained as tau B equals Fyw divided by root 3 tau W square. So 250 by root 3 times 1.4 square will be 73.642 Newton per millimeter square. Next, shear force corresponding to the wave buckling VCR will be obtained as dTw times tau B. That turns out to be 883.704 kilonewton, which is less than ultimate design shear force V, that is equal to 1191.312 kilonewton. Hence it is unsafe. That's why we have to revise our trial section. Let us revise the wave thickness from 10 to 12 millimeter. So for the revised wave thickness, elastic critical shear stress turns out to be 96.708 MPa. Non-dimensional wave slenderness ratio for shear buckling stress tau W turns out to be 1.222. So the shear stress corresponding to the buckling for tau W greater than 1.2 will be equal to 96.658 MPa. So the shear force corresponding to wave buckling VCR will be D times TW times tau B, that is equal to 1391.875 kilonewton, which is greater than the ultimate design shear force V, that is equal to 1191.312 kilonewton. So this section is safe. Then we are required to check for lateral torsional buckling. Since the compression flange of the girder is laterally restrained all throughout, we are not required to check for lateral torsional buckling in this case. Then we will go for flange to wave connection. The maximum shear force at the junction of wave and flange is given by QW equals V times AF times Y prime divided by 2 times IZ, where IZ is obtained as the moment of inertia of the section, and that turns out to be 1.081 10 to the power 10 millimeter 4 once we apply the magnitude of all the parameters in this expression. QW then turns out to be V, AF and Y prime divided by 2IZ. When we apply the magnitude of all the parameters, it is 0.406 kilonewton per millimeter. So let us provide a weld of size S equals 6 millimeter. Ks will be 0.7 times 6, that is equal to 4.2 millimeter. Strength of the weld per unit length FWD will be equal to 4.2 times 250 times 10 to the power minus 3 divided by square root of 3 times 1.25, that will be equal to 0.485 kilonewton per millimeter, which is greater than the magnitude of QW, that is 0.406 kilonewton per millimeter. So we can proceed with 6 millimeter continuous fillet welds on either side. So this is the section of the plate girder having wave thickness of 12 millimeter, flange thickness of 30 millimeter and depth of 1200 millimeter. The flange width is 400 millimeter. We can go for intermediate stiffness. Since the ratio of D by T equals 100, which is greater than 85, vertical stiffeners will be required. Adopting the spacing of the stiffeners C equals 1000 millimeter. The greater unsupported panel dimension of the web equals 1000 millimeter, which is less than 270 TW. So it means 3240 millimeter. The intermediate stiffeners are designed to have a minimum moment of inertia specified as I equals 1.5 T cube by C square. So 1.5 times T cube by C square can be obtained by providing the magnitude of all the parameters. That turns out to be having this much magnitude. Now if we go for using 12 millimeter thick plate, the outstand of the stiffeners should be not greater than 12T, that is 144 millimeter. If we use 12 millimeter by 120 millimeter plate, then I will be obtained as 691.2 10 to the power 4. That is greater than 448 times 10 to the power 4 millimeter. Connections of the vertical stiffener to the web can be determined now. The shear on the welds connecting the stiffener to web can be obtained as 126 T square by H, where T is the web thickness 12 millimeter, H is the outstand of the stiffener, that is 120 millimeter. So the shear on the welds connecting the stiffener to web will be equal to 126 T square by H, that turns out to be 151.2 Newton per millimeter. Size of the weld S can be obtained as 151.2 divided by 0.7 times 158, that is equal to 1.37 millimeter. Effective length of the weld should be not less than 10T, that is 120 millimeter. So we can proceed with providing 120 millimeter long 5 millimeter fillet welds alternatively on either side. The next step will be design of the steel truss. We have considered a Warren truss of 6 panels, each of the panel having a panel length of 5 meter. The span of the truss is 30 meter, height of the truss is 1/6 of the span, that is 5 meter. Dead load due to deck slab, wearing coat, stringer beams and cross girders acting at each node is 180.3 kN. We can approximate it to be 181 kN. Self-weight of the truss will be 0.15 L plus 5.5, that is equal to 0.15 times 30 plus 5.5 equals 10 kN per meter. Self-weight at each node point will be 5 times 10, that is equal to 50 kN. So the total dead load will be 181 plus 50, that is coming to be 231 kN. Live load is IRC class AA loading. The maximum bending moment is produced when the class AA vehicle is closest to the main girder. The maximum load transferred when one track is at 1.625 meter from the edge of the curve is shown in this diagram. From where this 1.625 is coming here? Because the wheels are expected to be having a clearance of 1.2 meter minimum and wheel imprint dimension is 0.85. So the center line of the wheel is going to be at a distance of 1.2 plus 0.85 by 2, that is equal to 1.625 meter far from the curve. The maximum live load can be obtained from the loading diagram, and that turns out to be 438.51 kN, which can be approximated as 439 kN. We can consider an impact factor of 1.1. So the maximum live load including impact will be 439 times 1.1, that is equal to 483 kN. The average uniformly distributed loading will be 483 divided by 3.6, that is the wheel length. So that is equal to 134.17 kN per meter, which can be approximated as 135 kN per meter. Forces in the members of the truss is determined when a rolling load of length 3.6 meter, which is shorter than the span length of 5 meter, rolls on the bridge. We can go for drawing the influence line diagrams for the forces in various members of the truss. We can see that's how the influence line diagram of the members L0, L1, L1, L2, L2, L3, U0, U1, U1, U2, and subsequently U3, U2, L0, U0, U0, L1, L1, U1, U1 L2 and L2 U2 are drawn. The name of the members are shown in this diagram. You can try to draw the influence line diagram for this loading on your own by referring to the last lecture. Next, we will first try with member L0 L1, which is this member, the first member in the bottom chord. Taking the moment about U0, influence line ordinate at U0 can be obtained as dm can be taken about U0 divided by the perpendicular distance, that can be obtained as 0.46. Then the influence line ordinate at L1 will be obtained as 0.46 times 25 by 27.5, that is equal to 0.416. Using the influence line diagram, the force due to dead loads will be 231 times 0.416 plus 0.33, 0.25 plus 0.16 plus 0.08, that is equal to 286 kilonewton in tension. So the force due to live loads can be obtained as 0.5 times 0.416 plus 0.366, that is to be multiplied by 3.6 times 135, that is equal to 190 kilonewton in tension. The next member is member L1 L2. Taking moment about U1, influence line ordinate at U1 will be 7.5 times 22.5 divided by 30 times 5, that is equal to 1.13. So the influence line ordinate at L1 will be 1.13 times 5 by 7.5, that is equal to 0.75. Influence line ordinate at L2 will be equal to 1.13 times 20 by 22.5, so that is equal to 1. So using the influence line diagram, force due to dead load will be 231 times 0.75 plus 1 plus 0.75 plus 0.5 plus 0.25, that is equal to 751 kilonewton tension, and force due to live load will be 0.5 times 0.88 plus 0.94 times 3.6 times 135, that is equal to 442 kilonewton tension. Next member is member L2 L3. Taking moment about U2, influence line ordinate at U2 will be 12.5 times 17.5 divided by 30 times 5, that is equal to 1.46. Influence line ordinate at L2 will be equal to 1.46 times 10 by 12.5, that is equal to 1.17. Influence line ordinate at L3 will be equal to 1.13 times 15 by 17.5, that is equal to 1.26. Using the influence line diagram, force due to dead loads will be equal to 231 times 1.17 plus 1.26 plus 0.58 plus 0.84 plus 0.42, that is equal to 989 kilonewton in tension. Force due to live load will be obtained as 0.5 times 1.13 plus 1.11 times 3.6 times 135, that is equal to 544 kilonewton in tension. Next member is member U0 U1. Now U0 U1, as we can see in the drawing, is the first member in the top chord. We have done the load calculation for L0 L1, L1 L2 and L2 L3. Because the truss is symmetric, we can proceed with the load calculation of the half truss. For U0 U1, taking moment about L1, we can find out about influence line ordinate at L1 to be 5 times 25 divided by 30 times 5, that is equal to 0.83. Using the influence line diagram, force due to dead load will be equal to 231 times 0.833 plus 0.67 plus 0.5 plus 0.33 plus 0.17, that is equal to 578 kilonewton in completion. Force due to live load will be equal to 0.5 times 0.735 plus 0.883 times 3.6 times 135, that is equal to 381 kilonewton in completion. Member U1 U2 will be the next one. Taking moment about L2, influence line ordinate at L2 can be obtained as 10 times 20 by 30 times 5, that is equal to 1.33. Using the influence line diagram, force due to dead load will be 231 times 0.66 plus 1.33 plus 1 plus 0.66 plus 0.3, that is equal to 920 kilonewton in compression. Force due to live load will be 0.5 times 1.17 plus 1.33 times 3.6 times 135, that is equal to 608 kilonewton in compression. Next member is member U2, U3. Taking moment about L3, influence line ordinate at L3 will be 15 times 15 by 30 times 5. That is equal to 1.5. So the influence line diagram can help us to determine the force due to the dead load, called to be 231 times 0.5 plus 1 plus 1.5 plus 1 plus 0.5. That is equal to 1040 kilonewton in compression. Force due to live load will be obtained as 0.5 times 1.5 plus 1.32 times 3.6 times 135. That is equal to 686 kilonewton in compression. Next member is member L0, U0. Force in L0, U0 is governed by the shear force in panel L0, L1. So the influence line ordinate at L1 will be 30 minus 5 by 30 sec theta. So that is obtained to be 25 by 30 times 1.13, that is equal to 0.94. Using the influence line diagram, force due to dead load can be obtained as 231 times 0.94 plus 0.75 plus 0.56 plus 0.37 plus 0.19. That is equal to 650 kilonewton in compression. Force due to live load will be obtained as 0.5 times 0.94 plus 0.8 multiplied by 3.6 times 135. That is equal to 423 kilonewton in compression. Next member is member U0, L1. Force in member U0, L1 is same as in L0, U0 but with different sign. So that is why the calculation steps will be entirely same and the type of the force will be different. So the dead load induced forces in member U0, L1 will be 650 kilonewton in tension, and force due to live load will be 423 kilonewton but in tension. Member U1, L1 will be the next member that is governed by the shear force in panel L1, L2. Influence line ordinate at L1 will be 5 by 30 multiplied by sec theta. So it equals 5 by 30 times 1.13, that is equal to 0.19. Using the influence line diagram, force due to dead loads can be obtained as 231 times minus of 0.19 plus 0.75 plus 0.56 plus 0.375 plus 0.187, that is equal to 389 kilonewton in compression. Force due to live load can be obtained as maximum compressive force equals 0.5 times 0.72 times 3.6 times 135, that is equal to 175 kilonewton. Maximum tensile force will be 0.5 times 0.19 times 1.22 times 135 plus 0.5 times 0.09 plus 0.19 multiplied by 2.38 times 135. That is equal to 61 kilonewton. Next member is member U1, L2. The force in member U1, L2 is same as U1, L1 but with different sign. So that's why the force due to dead load in this member will be 389 kilonewton in tension, and the maximum tensile force will be 175 kilonewton while the maximum compressive force will be 61 kilonewton. The next member is member U2, L2. Force in U2L2 is governed by the shear force in L2L3. Influence line ordinate at L2 will be obtained as 10 by 30 times sec theta, that is equal to 10 by 30 times 1.13 equals 0.377. Influence line ordinate at L3 can be obtained as 15 by 30 sec theta equal to 15 by 30 times 1.13, that is equal to 0.565. Using the influence line diagram, the force due to dead load can be obtained as 31 times minus of 0.377 minus of 0.189 plus 0.565 0.376 plus 0.188. That gives us 130 kilonewton in compression. Force due to live load will be obtained by using the inference line diagram. The maximum tensile force will be 0.5 times 0.377 times 2 times 135 plus 0.316 plus 0.377 divided by 2 multiplied by 1.6 times 135, that is equal to 126 kilonewton. Similarly, maximum compressive force can be obtained as 0.5 times 3 times 0.565 times 135 plus 0.565 plus 0.542 by 2 multiplied by 0.6 times 135, that gives us 160 kN. The member force in U2L3 will be same as in U2L2 but with different sign. So the dead load induced forces in member U2L3 will be 130 kN in tension. Maximum compressive force due to live load will be 126 kN and maximum tension force due to live load will be 160 kN. So we can tabulate the design forces in the trusses. First, the forces in the members due to live load and due to dead load of compression and tensile nature are tabulated. Subsequently, the combined loads are calculated and the maximum and minimum values are determined. So from there, the critical load for each member is summarized in the last column. Now this critical load will be required to be provided with a factor of 1.5 so as to obtain the design force. The factor design force for each of the member will be used for design of each of the member. So first member that we are going to consider is member L2, L3. If we go back, you will see that L0, L1, L1, L2 and L2, L3, these are bottom chord members. And the maximum critical load is obtained to be 1530 kilonewton. So L2, L3 is the critical member which can be picked up for design. Now U0, U1, U1, U2, U2, U3 are the top chord members and the critical force here is 1726 kilonewton. That can be picked for the design of the top chord. Similarly, the diagonals U0, L0, U0, L1, U1, L1, U1, L2, U2, L2 and U2, L3. We can look for the critical load in the diagonals and identify which of the diagonals we are going to select. Let's go for member L2, L3, the bottom chord member. The factor design force in the member L2, L3 of tensile nature will be 1.5 times 1530 kilonewton, that is equal to 2295 kilonewton. So let's try a section as follows. We can go for two plates of 350 mm width times 12 mm thickness, that is going to have a cross sectional area of 8400 mm square. Along with that, we can consider four angles of 75, 75, 10. That is going to have a cross-sectional area of 5608 mm square in total. So the total cross-sectional area comprising the plates and the angle sections are going to be 13708 mm square. So the design strength of a member under axial tension TD is the lowest of the design strength due to reading of the cross section, rupture strength of the critical section and block shear. The design strength of a member under axial tension due to yielding of the cross section TDG will be equal to AG times Fy by gamma m0, where gamma m0 is the partial safety factor for failure in tension by yielding, equals 1.1. AG is the gross cross-sectional area, Fy is the characteristic yield strength of steel. So TDG can be obtained by applying the magnitude of the parameters and that turns out to be 3115 kN. Design rupture strength of the critical section TDN is obtained to be 0.9 times AN times FU by gamma M1, where AN is the net root area of the threaded section, that is taken to be the gross area of the section 13708 mm square. Gamma M1 will be equal to partial safety factor of the failure governed by ultimate stress, that is equal to 1.25. Fu is the ultimate stress of the material, that is assumed to be 400 MPa. So TDN equals 0.9 AN times Fu by gamma M1 can be obtained by providing the magnitude of all the parameters, and that turns out to be 3948 kilonewton. So the design strength of a member under axial tension TD equals the lowest of the two, that is equal to 3115 kilonewton, which is higher than the factor design tension force equals 2295 kilonewton. Hence our design is safe for the member. Next we are going to design the top chord member U2 U3. The factor design force in member U2 U3 of compressive nature P equals 1.5 times the loading, that is 1726 kilonewton. That turns out to be 2589 kilonewton in completion. Let's try a section containing one top flange of 500 millimeter width and 8 millimeter thickness, that is going to have a total area of 4000 millimeter square, and two ISMC sections of ISMC 350, that is going to have a total area of 2 times 5366, that is 10732 millimeter square. The total cross-sectional area of the two type of section will be 14732 millimeter square. The design compressive strength PD of a member is obtained as AC times FCD, where the design compressive stress FCD of axially loaded compression members can be calculated as FCD equals Fy by gamma M0 divided by phi plus square root of phi square minus lambda square. Here, phi is a function of alpha and lambda is non-dimensional effective slenderness ratio obtained as square root of Fy times KL by R square divided by pi square. Here, KL by R is effective slenderness ratio, that is a ratio of effective length KL to the radius of gyration R. Alpha is considered to be imperfection factor, that is dependent on the buckling class and the thickness of the flange. Gamma M0 is partial safety factor for material strength, that is taken to be 1.1. Radius of gyration Rxx is considered to be 0.4d, that is 0.4 times 350, that is 140 millimeter. Radius of gyration Ryy is taken to be 0.34b, that is considered to be 0.34 times 500, that is equal to 170 millimeter. Effective length is considered to be 0.85 times length of 5 meter, that is equal to 4250 millimeter. So effective slenderness ratio will be KL by R, that is equal to 4250 by 140, the least of the two, that is equal to 30.36. For flange thickness of 8 millimeter, that is less than 40 millimeter, and buckling class B, alpha, that is imperfection factor as per IS code is 0.34. So lambda can be obtained as shown here by providing the magnitude of all the parameters, that is turning out to be 0.34. So for the given value of alpha and the calculated value of lambda, phi can be determined from this expression, and that turns out to be 0.58. So FCD can be obtained by applying the magnitude of all the parameters in this expression, and it is calculated to be 216.47 MPa. So the design compressive strength of the section PD can be obtained as AC times FCD. AC we know that is obtained from the two types of sections, that is considered as 14732 millimeter square. FCD we have just now computed to be 216.47 MPa. So from there, PD turns out to be 3189 kilonewton, which is greater than the factor design compression force equals 2589 kilonewton. So we can say that the design is safe for this member. The next member that we are going to consider is a diagonal tension member, U0 L1. The factor design force in the member U0L1 T equals 1.5 times 1073 kilonewton, that is equal to 1610 kilonewton. Let's try a section of a plate of 280 millimeter width times 15 millimeter thickness with a cross-sectional area of 4200 millimeter square and 4 angles of 75, 75, 10 with a cross-sectional area of 5608 millimeter square. So the total cross-sectional area will be summation of both, that is equal to 980 millimeter square. Now we have discussed that the design strength of a member under axial tension is the lowest of the design strength due to yielding of cross section or a rupture strength of the critical section and the block shear. So the design strength of a member under axial tension due to yielding of cross section TDG can be obtained as AG times Fy by gamma m0, where gamma m0 is partial safety factor for failure in tension by yielding, that is equal to 1.1. TDG hence can be obtained by providing the magnitude of all the parameters, that is equal to 2229 kilonewton. The design rupture strength of the critical section TDN can be obtained as 0.9 times AN times FU by gamma m1. AN is the net root area of the threaded section taken to be the gross area of the section, that is equal to 9808 millimeter square. Gamma m1 is the partial safety factor for failure governed by ultimate stress, that is equal to 1.25. Fu is the ultimate stress of the material, that is taken to be 400 MPa. So from there TDN turns out to be 2825 kilonewton. Block shear we have not considered for welded section. The design strength of the member under axial tension TD is obtained as a minimum of the three sources, that is equal to 2229 kilonewton, which is greater than the factor design tension force of 1610 kilonewton. Hence the design is found to be safe for the diagonal tension member. Member U1L1 is a diagonal member which is found to be critical when it is under compression. So the factor design force in member U1L1 is obtained as 1.5 times 564 kilonewton, that is equal to 846 kilonewton in compression. Let's try a section comprising one top flange of 280 millimeter width and 10 millimeter thickness, that is going to have an area of 2800 millimeter square. 4 angles of 100, 112 with a cross-sectional area of 4 times 2106, that is equal to 9036 square millimeter. The total cross-sectional area AC equals 11836 millimeter square by summing both the area. The design compressive strength PT of a member can be obtained as AC times FCD, where AC is the cross-sectional area of the member. FCD can be obtained as we had discussed earlier for axially loaded compression member by using this expression. Here phi is a function of alpha and lambda. Lambda is non-dimensional effective slenderness ratio dependent on the effective slenderness ratio, that is equal to the ratio of effective length KL divided by the appropriate radius of gyration R, and alpha is imperfection factor. Now gamma m0 is partial safety factor for material strength taken to be 1.1. Radius of gyration for the section is taken to be 0.39 d, that is equal to 109 millimeter. Radius of gyration RYY taken to be 0.21 b, that is equal to 44 millimeter. So the effective length KL is taken to be 0.85 times the length, that is 4760 millimeter. Effective slenderness ratio will be KL by R, that is equal to 108. List of the two has been considered. So for TF equals 10 mm, which is less than 40 millimeter, and buckling class C alpha, that is imperfection factor, will be 0.49. So lambda can be determined as 1.48 from the expression. Phi as a function of lambda and alpha can be obtained at 1.91. So FCD can be obtained by providing the magnitude of all the parameters, that is equal to 72.91 MPa. So from there TD equals AC times FCD. So which is obtained to be 862.96 kilonewton, which is found to be greater than factor design compression force equals 846 kN, as the design is safe. Here, for every steel design, we have followed IS 800 2007. The detailed drawing of the truss, consisting of the cross-sectional details of the typical junctions of the members, are shown. For the truss, the detailing of members at U0, U2, L2 are shown. We can have a look at the cross section of the steel truss bridge, showing the clear roadway width of 7.5 meter, then RC deck slab of 200 millimeter thickness, bearing coat of 100 millimeter thickness, stringer beams ISWB 550, then the distance between center of each of the stringer beams are 1.875 meter, plate girder of 400 mm times 1200 mm. Then the trusses are shown here. That's all for today's discussion. If you have any question, please feel free to put your queries in the discussion forum. We are going to revert back to you quickly. These are the references that we have followed. Thank you so much. We are ending our class here.